Okay, so welcome everybody. It's a pleasure to have Salome Mtchedlidze. Yes, we decided to do it this way because otherwise it would be impossible for me to pronounce the surname in the right way. So Salome did a master and bachelor in Georgia, Tbilisi, and then she joined a joint PhD program between Göttingen in Germany and Tbilisi. Then she moved for a short period to Stockholm at DIFA, and then she joined as a postdoc the group Franco Basta, working on magnetism in general, and then she will tell us. So please, you have 20 minutes plus 5, more or less, and I will tell you when 5 minutes.
Okay, great, thanks. Yeah, hello everyone. Yeah, it's a pleasure for me to talk about our research projects. And I will also take a chance, since Franco is not here, to say thanks to him. And in general, it's been a pleasure to work in this university with Franco and with people here. So yeah, I will be talking about magnetic fields, and well, since this is a short talk and I was told to give a proper introduction, I will try to, oh, sorry. Oh no. Sorry. Yeah, I will try to talk about evolution, observations, and signatures of cosmic magnetic fields. So when we talk about cosmic magnetism, usually first the small scales come in our mind. So stars and planets with which we have direct measurements for measuring magnetic field, and Still-Zeeman splitting is the direct method with which we measure magnetic fields in stars. But then things get more exciting and fun when thinking about magnetism even on larger scales in extragalactic space. And yesterday, Chris and I found, well, first, we realized that I should mention Jansky, who basically made first detection of first radio emission from our own galaxy. And yeah, I should have mentioned this because most of what we know about extragalactic magnetic fields comes through detection of radio waves. And then another great observations, and this is how the map of this radio emission was looked at the time from Reber's observations. Yeah, well, it was actually detection of first extragalactic magnetic fields in the Cygnus, well, detecting Cygnus galaxy, or radio emission from that galaxy. But at that time, we didn't know that this was actually a synchrotron emission, which itself was tracing magnetic fields. So yeah, synchrotron emission, which is basically just electrons gyrating along magnetic field lines and emitting this radio, the synchrotron emission in the radio waveband, is one of the powerful methods with which we trace magnetic fields on large scales, along with Faraday rotation that I will talk about a bit later. And so we saw how maps looked like around century and a bit more ago. And now this is what we are observing. So maybe you have already seen similar pictures. Well, not pictures, but images. So these are, again, synchrotron emission, but now detected on huge scales, on galaxy cluster scales, and even beyond. This is all called bridges, and we call these bridges basically this space between galaxy clusters, which we now see to be magnetized as well because we detect the synchrotron emission from these scales as well. And then we naturally raises a question whether magnetic field exists even on larger scales. In particular, whether there can be magnetic fields even in cosmic voids. And yes, and this was actually a question that also motivated me or attracted me when I was starting my PhD, because it's interesting to know whether magnetic fields exist even in on such large scales. And the observation, so I will try to very briefly discuss these observations, for which give us some hints that magnetic fields can exist even in voids. So blazars that are very distant objects emit high energy gamma rays, which are actually attenuated before they reach us. And because this process is taking place on these very large scales, then probability that during emission and during propagation, these gamma rays produce electron-positron pairs in voids is very high. So basically, these high energy gamma rays produce electron-positron pairs while interacting with extragalactic background light, and then they are producing they are scattered themselves with cosmic microwave background photons, producing secondary emission. And then, if there is magnetic field on such large scales, they can deviate these electron-positron pairs and suppress this secondary emission from our telescope. So this would be the spectrum, roughly how it would look like when magnetic fields are affecting this propagation of secondary gamma rays. And so in principle, we are expecting that around these primary gamma rays, we should also see halo kind of picture because of the secondary cascade. We do observe this suppression of the spectrum, but we have not yet detected this halo, but this itself gives us constraints on the magnetic field strength in the void, which is at the moment around 10 to the minus 14 or 10 to the minus 16 Gauss. So then this leads us to another question. How these magnetic fields could have been generated, even not assuming them to be in voids, but even on galaxy cluster scales. So the consensus currently is that there should have been some initial Wicksed fields that would then be amplified by dynamo action so that they reach micro-Gauss strength fields in galaxy clusters. And dynamo requires turbulence, and turbulence in principle could have been present both in the early universe and then later during reionization and structure formation as well. And just to also briefly say, dynamo is basically a mechanism which converts kinetic energy into magnetic energy and leads to exponential growth of magnetic fields, just basically a randomly stretching and bending magnetic field lines. So if we look at the magnetic field evolution equation, so here V is the velocity of the fluid and sigma is the conductivity, and this equation is written in co-moving coordinates. So the first term in the right-hand side is responsible for the growth of magnetic field, while the second term is responsible for diffusion. And if we look at this equation, and if we assume that there were no magnetic fields, so B equals to 0, then we see there is no source term, so magnetic fields could not grow. So that's why we need some initial weak fields so that they can be amplified. But how then these fields are generated? So there, we think about these generation scenarios kind of in a similar fashion as cosmologists think about structural formation. So this could happen either in a top-down fashion, meaning that you could have very large-scale field, like field correlated on very, very large scales, and then this would be fragmented or amplified on smaller scales, so that magnetic field still exists on these very large scales, or in a bottom-up fashion, which means that you had first this seed field generated on very small scales, and then it's amplified and transported some transfer mechanisms into larger scales. Although, of course, in this case, we don't know how volume filling these magnetic fields are, or whether they can fill the voids and the entire universe. So when we think about generation of seed fields in the early universe, we usually refer to primordial magnetic fields, or we call them primordial magnetic fields. Or if we think about generations of seed fields in the late universe during reionization and structure formation, we call them astrophysical seed fields. And yeah, so again, if magnetic fields have been generated purely from an astrophysical scenario and then was growing in a bottom-up fashion. So then we would need some transfer mechanisms, such as, for example, magnetized jets or galactic winds that would transfer magnetic fields from galaxies into IGM. So an example of simple example of bottom-up magnetization scenario would be so-called charge separation processes. So it's a kind of classic mechanism which would take place both in the early universe and in the late universe as well. So because if we had charges or quasi-neutral plasma, and also some non-equilibrium processes, and then these charges could be separated so that first initial seed fields are produced and then they could be amplified. So another not very classic scenario is that top-down scenario in which magnetic field already exists during inflation or is produced during inflation, is when one considers coupling of the inflaton-like field or scalar field and electromagnetic action during inflation. So in this case, magnetic field in principle could be correlated even on larger scales, larger than the Hubble horizon. And we characterize, I already mentioned this word, maybe coherent scale, and just to know what we're talking about, very briefly define it. So it's well, first we need to define the magnetic energy power spectrum. Here, well, it's just the energy in Fourier space summed in the spherical Fourier beams. And with magnetic energy power spectrum, we define the correlation length, which is just the characteristic scale, and integrated power spectrum weighted by the inverse wave number. So then when we think of about this top-down scenario, we think that, okay, these magnetic fields have been generated on these very large scales, and then turbulence and dynamo in the early universe could already sustain and amplify or further amplify them. And yeah, so this is just the formally that you take the electromagnetic action and then couple to scalar field, so that during inflation, we in the classic Friedman elementary over Solomon space, electromagnetic fields just decay during the expansion, and this coupling is necessary in order them not to decay and not to decay basically. So yeah, just a little break, and why we are interested in magnetic fields at all, and why we care about understanding their origin. So if no matter they are astrophysical or primordial, they would leave their signatures, for example, on the evolution of IGM. So this is just the temporary sketch for the this is actually ionization fraction, but yeah, both on the ionization fraction as well on IGM temperature evolution. So the red line in this and other sketches just show classic evolution of ionization fraction or some other quantities, and this would be how magnetic fields would affect evolution. Yeah, this plot is produced for primordial magnetic fields, but in general, if even from astrophysical seed fields, they could also affect because of diffusion and dissipation in the IGM, so temperature of the IGM could increase. And also there is continuous debate, I would say, whether magnetic field suppresses or promotes star formation. So some studies found that they can increase star formation rates, or some simulations find that they suppress star formation. And also more and more interesting things come from primordial magnetic fields. So if they exist and they affect processes in the early universe, and actually, these are not really new studies. I think it started at least 30 years ago, that people started thinking about generation of gravitational waves from primordial sources, and one of sources is actually primordial magnetic fields. And this is just the sketch, and this is the range where the pulsar timing arrays are able to detect gravitational waves from early universe sources. And also, we expect that PMFs would affect CMB and matter power spectrum. And also, at the moment, I think in the CMB, it's on very high K, so we would not be able to detect. But yeah, maybe on the matter power spectrum, it's more possible. Yeah, so what we study, or on which branch our studies are. So initially, when I started PhD, we wanted to connect evolution of primordial magnetic fields in the early universe with the evolution of magnetic fields during structure formation, basically to reconstruct the full picture of the evolution of PMFs. Because we already had simulations, pure hydrodynamic simulations that we are studying with which primordial magnetic field evolution has been studied for the early Università. And then we wanted to basically use these simulations or outcome of this of their simulations as an initial conditions for our simulations. Although we realize that it's a very challenging task, because as you can imagine, these are different scales, and in one simulation you cannot really cover all of these processes, because, yeah, as I said, in the early universe you can just model magnetic field evolution with pure MHD, while during structure formation you need cosmological code. So, and then at the end, in principle, our research question was to study just different primordial magnetic field models and study their signatures and think of whether we could distinguish these different primordial magnetic field models. So we actually studied the evolution of these fields in the cosmic web, so having large blocks and just studying general properties and evolution of these fields. And then on the other hand, we also studied their evolution within galaxy clusters. But today I will just very briefly, I will focus on cosmic web project, and also the project that I'm working now with Franco. I wanted to have results on this as well, but sadly I don't have them yet. So the idea of this current project is to study also the magnetization of the IGM from astrophysical sources. So if we have magnetized jets from galaxies, how they would magnetize the IGM. Yeah, and from this, since I will, at the end of the talk, I will mention some implications of the cosmic web project. I just wanted to say the main result of this project. So here I'm showing the magnetic energy power spectrum at initial redshift of our simulations at final redshift. So here you see our initial conditions. So these are basically just different primordial magnetic field models having different correlation lengths initially, and plus the uniform model, which you don't see here because its power spectrum is picked at k equals 0 wave number. So basically this is just constant magnetic field model, while these are just stochastic distributions with certain coherent scales. And with these initial conditions at final redshift, we observe this solid line. So just to give you an idea, this scale here is roughly galaxy cluster scales, and everything in the left is a larger scale. So basically we see that fields, if we start with different initial structure of magnetic fields, and we would obtain different structure on these large scales as well. So they should lead some signatures on these large scales. Yeah, and these are just illustration. So snapshots from our simulations, the magnetic field, projected magnetic field picture images. So in the top you see the magnetic field strengths for the larger scale model, for large scale PMF, and on the bottom you see from small scale model. And basically we see that growth of magnetic field is more efficient, and we see higher field strengths from these large scale models, as is also expected from this plot, than from this smaller scale field. So yeah, then the next question we had, or as I mentioned also earlier, was how we can distinguish these different fields, or whether we can have any hints from observations. And for this, we used rotation measure analysis. So we know that Faraday rotation effect is the effect that when polarized light passes through magnetized medium, such as, for example, magnetized galaxy cluster, its intrinsic polarization plane is rotated, so that we get a difference between this intrinsic and measured polarization planes. And this effect is quantified, so-called rotation measure, which itself is an integrated quantity of line of sight magnetic field strengths and electron number density. So it traces line of sight magnetic fields. But the challenge here is that, or for the detection of large-scale magnetic fields, is that we are interested on the RM in the IGM. So basically, along the line of sight, we have contribution from magnetic fields in this effect from the source magnetic field, from the IGM, and from our own galaxy as well. So that we want to basically exclude the other contribution and focus on this RM in the IGM. And this is not really a new idea from observation point of view to use this technique. And this was already in the past century has been used. And then also in the recent years, it's re-emerged because of higher sensitivity of radio observations. And yeah, so this is just an example how the RM map looks from observations. So these different colors means just negative or positive values of RM. And then one of the statistical quantities that we study is the mean rotation measure. And then we can compare from observations of obtained mean RM, or RMS actually, with what we see from simulations. And yeah, just try to be quick. In order to compare simulation results with observations, we need to span our results or simulation results until higher redshift. And for this, we stack cosmological boxes and study the RM in this so-called light cone, with this light cone technique. So I don't think I will have time for this, or yeah, maybe I can just very briefly show how this stacking procedure looks. Basically, it's just the snapshots before at certain redshift, and then you stack them and integrate along the whole line of sight. Here, just an example is for the density field for lower redshift, but in our actual analysis, we reached redshift 2 or 3. And this is also how our maps, rotation measure maps look for large scale and smaller scale primordial magnetic field models. And yes, also wanted to show the recent previous studies where the RM evolution with redshift has been studied. And in principle, in all of these studies have already been shown that depending on what type of magnetization scenarios you take into account, you get different evolution, different RM versus redshift evolution. And this is also what Franco sees also in his recent work. He is considering both primordial and astrophysical sources, while in our work, we focus only on primordial magnetic fields, but for the first time studied how the coherence scale of primordial magnetic field affects this RMS evolution. And what we see, so here you see the RM versus redshift for different primordial magnetic field models, having different coherence scales initially and with also a uniform field. And we also overplot the results from observations as obtained from Carty et al. And what we see that all RMs increase with redshift for all PMF models, but for example, this model, I'm not sure if it's well seen here, shows more saturation at high redshifts or flattening. And also its amplitude or these RMS values are better matches with observations. And yeah, so we also saw that the small scale fields, which is like these 3 models, also show degeneracy, meaning that the slopes of the RMS evolve in a similar way. Yes, yeah, okay, so I forgot, I also overplotted here astrophysical scenarios from Franco's work, and what we see actually is that compared to primordial magnetic field models, they show also this flattening at high redshift, which is also less seen from these observations, and now even less seen from new study from Carretti et al. So yes, I think I should finish. So I don't, I don't discuss this, and then I will just briefly say summary. Yeah, so just to summarize, I talked about how magnetic fields could grow, and what type of scenarios we are currently considering about their amplification. And then in this talk, we focused on the evolution of primordial magnetic fields. We also said that it's challenging to reconstruct the full picture of PMF evolution from the early universe till now, but we are trying to study different coherence scales and then exclude some of the models. And currently, we are also working on better a comparison of our simulation results with observations. And also just one of main takeaway from this talk, which I maybe should have emphasized more, is that our study shows that PMFs with coherence scales smaller than 3.5 megaparsec are disfavored from our study. Yes, I think that's all what I wanted to say. Yeah, well, that's it. Thanks.
Thanks a lot for the slides, really nice. So just a question about you, when you inject, you use different ingredients, different primordial fields, no? Then you have the prediction for the redshift zero, right?
Yes.
So can we already exclude some of these models with the limits that we have from lasers, or in case of how do you need to improve the limits?
Yes. I think as far as I know, Franco and Emmanuel Meyer, they have had recently or a year ago a work where they compared uniform magnetic field model and I think stochastic models with gamma ray observations, and they excluded uniform models.
Exclude the astrophysical scenarios.
Or astrophysical, yes. Yeah. So yeah, in our case, yeah, actually we started collaboration with Andrei Neronov, his student, but we never ended up doing something like, yeah, we don't have any outcomes from there yet. So we haven't compared from our models.
Great box. I would like to ask you about how do you decide the resolution of the simulation with tensor?
Yes.
Which is required by the computational resource you have, or you did some resolution study?
Yes, so I think we did resolution study after we decided actually resolution. But yeah, actually that was so long time ago. Initially, yeah, I think I was just testing some simulations. And then I think once we defined more or less project idea that in this first project, we wanted to focus on larger scale. So we are not focusing on amplification within galaxy clusters. So we did not need any high resolution in galaxy clusters. So we.
But you should, if you want to resolve the turbulent dynamo in your MHD simulation, you need very, very small resolution, fine resolution if the magnetic field is very, very weak, because the RPN scale is very, very small. In that case, I think it can be smaller than parsec. So it's almost impossible to resolve the computation from femtogas or nanogas. So maybe, yeah, it's very.
Yes, but as I said, yeah, in the other study where we studied amplification in galaxy cluster, well, there as well, we did not have parsec resolution, we had kiloparsec resolution, but yeah, I agree with you that it definitely, in this case, we are not focused on, but maybe, so are you saying that it can affect also in filaments and in voids, how magnetic?
Yeah, also voids, maybe. Okay, so yeah, maybe in voids, it's not so important because maybe the turbulent dynamo is not the main process of but in filaments and clusters, yeah.
Thanks.
Yeah.
Other questions? Last question.
So could you show again the plot in which you have the spectrum of the magnetic field.
Yes. Yes.
Okay, so it looks like at the smaller scales of around clusters of galaxies, if I understand it, but the different models are more or less producing similar values.
Yeah.
Is this something that comes out natural from the evolution, or are you selecting models that are matching?
Yeah, so I think that's a really hard question for me because because I know that we studied also evolution of magnetic fields within galaxy clusters, as I said, with higher resolution, with zoom-in simulation. So there as well. So we saw that in that higher resolution simulations, we saw still differences between different PMF models. Although there has been, everyone believes that dynamo erases any imprint from PMFs in galaxy clusters, which can be the case if we really don't have enough resolution in our simulation. So I really cannot say anything. So I think it would be cool to have some other simulations. Yeah, but also it's challenging to reach really such resolution.
Okay, so let's thank the speaker again.